All right, so like I said, page 327 today, and we're going to continue with bisectors of triangles. And today we're going to cover angle bisectors. And the angle bisector theorem states that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So if you draw an angle on your paper, and we'll call it DBE. Bisector of an angle is a segment that splits an angle in half. So if we draw a ray right out of point B, and we try to get it through the middle of the angle, all right, B to, we'll call it B to F, it's called an angle bisector. If these two angles are congruent down here, then BF is an angle bisector. And what the theorem says is that if a point is on the bisector of an angle, so point F is on this angle, on this bisector, that it's equal distance from the sides of the angle. And what that means is if you drew a line from F to the side of this angle, all right, and then F to the other side of the angle, this is obviously not to scale, all right, and that segment is perpendicular to the side of the angle, then D to F would be congruent to E to F. Any point on a bisector is equal distance from the sides of the angle. All right, so if you had a point here and you drew a segment to the side of the angle and another segment to the other side of the angle, well, then those two pieces would be congruent as well. Any point that you draw on this angle bisector will be the same distance to both sides of the angle. Everybody see that? All right, and then there's a converse of that theorem. Oops. And the converse of that theorem states that if a point in the interior of an angle is equidistant from the sides, then it is on the angle bisector. It's going to end up being the same drawing. We can label the points differently. But just like yesterday, the tick marks and the angle arc marks will go on in a different order. So if we have this angle, again, I'm going to call this one ABC. The theorem says if a point in the interior of an angle is equidistant from the sides. So if we put a point in the interior of this angle, call it point D, and D to C is the same length as D to A. All right, so now we've got a point in the interior of an angle, and it's equal distance from the sides. The converse of the theorem says then it is on the angle bisector. That means that this point, if we put a line from B through D, then BD is an angle bisector, and it splits this big angle down here on the bottom in half. So all of the information remains the same, but in the last example, we put the arc marks on first. In this example, we'll put the arc marks on last. Okay? The order in which you can add the information changes, but all of the information remains the same. Okay? If a segment bisects an angle, then any point on that segment is the same distance from the sides. If a point is the same distance from the sides of an angle, then it's on the angle bisector. And that ray splits the big angle in half. So if you look down at example 3 on page 327, we got 3A, B, and C. And example 3A, you've got this looking picture. We've got point X right here. All right, so we got point X, we got point Y here, and we've got point W. You are told that both of these angles are 41 degrees. Sorry, 41 degrees. So if these two angles are congruent, that means that this segment ZX is an angle bisector. And if ZX is an angle bisector, then X to Y is the same distance as X to W. And you're told that X to W is 7, and you're asked to find X to Y. So in this case, how far is it from X to Y? 7. Good. All right, that's a point on an angle bisector. So if a point is on an angle bisector, then it is equidistant from the sides of the angle. Example 3B, we got this look. And now, here's how you're given the information. You got point J here. L, and you've got M. Now you're told that J to L is congruent to L to M. You're given this angle down here is 37 degrees. and you're asked to find the measure of angle JKL. All right, so if we go from J to K and back up to L, well, we have point L that is equidistant from both sides of the angle. So if a point is equal distance from the sides of the angle, then it's on the angle bisector. So if KL is an angle bisector, these two angles are congruent. So what's the measure of angle JKL? Good, 37 degrees. Those two angles are congruent to each other. Bless you. All right, and then the third type of picture that you're going to see today is, again, we've got another big angle. And then let's draw a ray coming out of the vertex. We're going to label this M, S, and P. M to S is 3x plus 5. S to P is 6x minus 7. And we're told these two angles are congruent. So we're using that same theorem. All right? If these two angles are congruent to each other, then JS, J to S, is an angle bisector. Any point on an angle bisector is equidistant from the sides of the angle. So M to S is congruent to S to P. Well, they're asking you for SP. So in order to find the distance from S to P, we need to solve for X. So we take 3x plus 5, set it equal to 6x minus 7, and we solve. So subtract 3x from each side. We get a 5 that's equal to 3x minus 7. Add 7 to each side. And 12 is equal to 3x. And then divide both sides by 3. So 4 is equal to x. So if 4 is equal to x and we need SP, we need 6 times 4 minus 7. And 6 times 4 is 24. 24 minus 7 is 17. So our SP is equal to 17. All right, does anybody have any questions? Points on an angle bisector are equidistant from the sides of an angle. If a point is equidistant from the sides of an angle, then it is on an angle bisector. All right, so your practice for today is going to be on page, it's going to start on page 329, 5 through 7, and then 21 through 26 on the next page.